Okay, we are asked here to evaluate the performance of a refrigerator. By steadily circulating a refrigerant at low temperature through passages in the walls of the freezer compartment, a refrigerator maintains the freezer compartment at -5 degrees Celsius when the surrounding air is at 22 degrees. The rate of heat transfer from the freezer compartment to the refrigerant is 800 kilojoules per hour. Essentially, this is the capacity of your refrigerator. It's able to remove 8,000 kilojoules every hour. Okay, and the power input required to operate the refrigerator is at 3,200 kilojoules per hour. Determine the COP of the refrigerator and what will be the COP of a reversible refrigeration cycle operating between the same two reservoirs. Essentially, we're being asked here or being required to determine the COP actual, okay, the actual COP of our refrigerator, and we are also being asked to COP of an ideal refrigerator, meaning operating at reversible, um, at really reversible refrigeration cycle. Now let me sketch here what are the you know parts of a refrigeration system. Essentially, you just need to have a heat exchanger. Let's call this hex heat exchanger. And this heat exchanger, essentially, this is where your what? The cold temperature will end. Okay, this is your cold reservoir. Essentially, this might be your this place here might be your okay cold reservoir. This might be your refrigerator mismo, okay, meaning this is the refrigerated space, and the heat will flow. We have a working fluid. The working fluid will absorb that heat, okay. We call this heat here QC, okay, because it comes from the cold reservoir. And after that, the the working fluid or the refrigerant will then be compressed, okay. It will enter a compressor, okay. It will be compressed by a compressor, of course, where the compressor, to run the compressor must be supplied with, we call this, not really fluid, but the compressor will be supplied with shaft work, okay. The compressor must have a shaft work added into it or supplied with work so that it can do the thing, the compression process, okay, normally in electrical form. Now after compression, the fluid will now be heated up, and it's now at higher temperature, high enough so that by having this another heat exchanger here, hex hex 2, like this is hex 1, this is hex 2, it will be able now to what, to release that heat, okay. It will now be able to release that heat to the hot reservoir. In this case, this is now your air, okay, like this is your surrounding air. Now, this is now the hot reservoir or hot reservoir. In this case, okay, hot reservoir. This case, this is at -5 here. This is at -5 degrees Celsius, the cold reservoir. Here we have here at what? We have here at 22. Temperature of the hot reservoir is 22. And after that, since the the refrigerant will now be able to release its heat, it will now cool down, and then it will then be allowed to pass through a throttling valve. Okay, a throttling valve essentially is a throttling valve essentially reduces the pressure of your, because here after the compression process is high pressure, okay, high pressure, and then after this valve it will then be, this valve will reduce the pressure, this is low pressure, and that's why the refrigerant will be cooled below -5, more or less below -5. That's why it's able to absorb heat from the -5 cold reservoir, and the complete, this is now a refrigeration set, okay. Heat pump really is just the same, but the idea is where heat came from and what you desire. In refrigeration, you are actually aiming for QC. You want to remove QC from your cold reservoir, because if you don't remove that, maybe you could not maintain your cold reservoir at -5. So in this case, how do you compute for COP? Well, COP is simply defined by what you desired, and what did you input to your system, okay. what is your desired output, or what do you want to perform if you have refrigeration? You want to remove QC. You want QC, okay? You want QC to be big, perhaps. What is your input? This system won't work if you don't supply the shaft work, okay? Don't supply that, okay? And therefore, in answer for the question, the first determine the COP of the refrigerator. In this case, the COP actual will then be, so in answer for the first question, what will be the COP? So simply COP actual, and for this case, it's simply equal to what? QC. How much? It's given here that the rate of heat transfer you're able to remove from the freezer compartment 8,000 kilojoules. So 8,000 kilojoules per hour. Okay. What is how much? How much power? How much work shaft do you supply? Well, or shaft work, you are supplying actually the refrigerator with, to operate that, you're supplying 3,200, okay, kilojoules per hour, and the actual COP of your refrigerator will be 8,000, okay, 8,000 divided by 3,200, that's 2.5, okay, that's the COP, 2.5. Now the second question is, what if you have a refrigeration cycle which is ideal, which in that case operates reversibly? So what will be its what? What will be its COP? Well, if you talk about ideal, then you can perhaps refer to Carnot refrigerator. In that case, note right that QC, if you do energy balance, right, that you could in this refrigerator, you can do what? If you do heat balance, energy balance, energy entering is QC plus the shaft work, it will leave as what? This is termed as QH, right? Will leave as QH. Entering is equal to leaving, steady state process or cyclic process. Therefore, from here, shaft work could just be rewritten as what? QH minus QC. Okay? And therefore, we'll have there QC over what? Shaft work is just QH minus QC. Okay? And in this case, okay. And if we divide everything by QC, what will happen? We'll have 1 over QH over QC minus 1, right? And for ideal or reversible process, this could be rewritten as for ideal, okay? For ideal reversible, this could be rewritten as 1 over, that's QH minus QC could be rewritten in terms of temperature, TH over TC minus 1. That ratio could be replaced that if the process is ideal or reversible, the whole refrigeration process. In that case, COP ideal, or for the reversible process or the Carnot COP, in this case will just be 1 over THTC minus 1. Okay? And what will that be? Well, TH, the hot reservoir, is 22. Be sure to convert that to what? To Kelvin. So that's what? 22 is 295.15 Kelvin divided by that by TC, which is negative 5. So negative 5 plus 273.15, that's 268.15. Okay, minus 1, and that gives us 295.15 divided 268.15 minus 1, 1 divided by that. It gives me a value of COP for an ideal refrigeration cycle, 9.93. The actual is only 2.5, which means that perhaps you can have still room for improvement, or you can really gauge how far you are from ideal. So studying refrigeration is actually cool. So just follow. Nothing really much to memorize. You just need to do balances, and COP is defined really not as difficult thing. It's just defined as what you desire over what you invested or your input. Thank you.